The core issue we're addressing is that the data we observe is often not a random sample of the population we actually want to study. This phenomenon is known as incidental truncation. It occurs when our dependent variable, let's call it y, is missing for certain observations because of the outcome of another related variable, z. A classic illustration of this is when we try to estimate the potential wages for all women. We can only observe wages for those women who actively choose to work. If their decision to enter the workforce is correlated with their potential earnings, then a standard ordinary least squares, or OLS, regression will yield biased and inconsistent estimates. The graph on the right visually represents this. The visible data points, representing working women with observed wages, lead a standard OLS estimate to draw a much steeper line than the true underlying population regression, which accounts for both working and non-working women. This biased line demonstrates that OLS only sees the tip of the iceberg, missing the complete picture. This problem clearly highlights why we need a more sophisticated approach.
This flowchart helps us navigate models for limited dependent variables. First, we ask if outcomes are observed for everyone. If yes, simple ordinary least squares, or OLS, is typically sufficient. If not, we then check if we have predictor variables for the group with missing outcomes. If we don't, a truncated regression might be appropriate, for instance, if a survey explicitly excludes low-income individuals. If we do observe predictors, the next crucial question is whether the data is missing due to a specific selection rule. If the data is simply censored, like top-coded income values, a Probit model is the right choice. However, if the data is missing due to a selection process, our analytical goal becomes paramount. If we aim to estimate potential outcomes, such as a non-worker's potential wage, we turn to the Heckman selection model. But if our goal is to estimate actual outcomes where zeros are meaningful, like healthcare expenditures, then a two-part model is more suitable. Each path leads to a specific modeling approach designed to handle different types of missing data or limited dependent variables. This slide provides a side-by-side comparison of the Heckman selection model and the two-part model, two crucial tools for handling selection bias. The Heckman model, accessible with the Heckman command in Faracode, is used to answer what-if questions, focusing on potential or latent outcomes. For instance, what would a non-worker earn if they had worked? It assumes that the unobserved factors influencing the decision to participate and the outcome are correlated, meaning the errors are not independent. It addresses this by using a mathematical correction involving the inverse Mills ratio to adjust the slope and account for the bias. In contrast, the two-part model, initiated by the 2PM command, investigates actual, observed outcomes where zeros are genuine and meaningful, such as how much does a person actually spend. This model assumes independent errors, meaning the decision to participate and the amount spent are distinct, separate decisions. Its mechanism involves multiplying the probability of participation by the expected amount to arrive at a total expected value. The key distinction lies in whether you're interested in potential outcomes with correlated errors or actual observed outcomes with independent errors. The Heckman model consists of two equations. The first is the selection equation, which is typically a Probit model. It models the decision to participate. Here, the decision is made if zi gamma plus u2I is greater than 0. The second is the outcome equation, which is a standard linear regression for the variable of interest, like wages. Crucially, we only observe the outcome yi if the condition in the selection equation is met. The source of selection bias is the correlation, denoted by ρ, between the error terms of these two equations, u1i and u2i. If ρ is not 0, the expected value of the error term in the outcome equation, u1i, is not 0 for the selected sample, which violates a key OLS assumption. Heckman's brilliant insight was to treat selection bias as an omitted variable problem. The process starts with the selection data, represented by z, which we use to estimate a Probit model on the probability of being in the sample, for example, the probability of working. From this Probit model, we calculate a new variable for each observation called the inverse Mills ratio, denoted by the Greek letter lambda. This variable captures the selection hazard, the likelihood of being selected into the sample given the characteristics. Finally, we add this calculated lambda as an additional regressor in our original outcome equation.
By controlling for lambda, we absorb the selection bias, and the new error term becomes well-behaved, allowing for unbiased estimation of our parameters. Heckman's core insight is that by calculating and including lambda as a control variable, the selection bias effectively disappears from the outcome equation. For the model to be reliably identified, we need what's called an exclusion restriction. This means we need at least one variable, let's call it z, that directly affects the selection decision but does not have a direct effect on the outcome. This variable helps the model distinguish the selection effect from the outcome effects. Without it, the model relies only on the nonlinear functional form of the Probit model for identification, which is statistically weak and can lead to fragile results due to high collinearity between the regressors and the inverse Mills ratio. Control variables, like education, are expected to affect both the decision to work and the wage offered. In the women's wage model, the presence of small children is a classic exclusion restriction. Having small children strongly affects a woman's decision to work, the selection, but it shouldn't directly affect the wage an employer offers her, the outcome. The command in Stata for implementing the Heckman selection model is simply Heckman. The basic syntax starts by defining the outcome equation, just like a standard linear regression. Here, we're modeling wage as the dependent variable, explained by educ and age. Following this, we use the select option to specify the variables for the selection equation, which models the decision to participate in the workforce. In this example, married, children, educ, and age are included in the selection equation. Notice the critical role of children here. It's included in the selection equation, but not in the main outcome equation. This makes children our exclusion restriction, a variable that influences the decision to work, but not the wage offered, which is crucial for proper model identification. So, this single command effectively sets up and estimates both the outcome and selection equations simultaneously. When applying the Heckman selection model in Stata, you have two primary estimation methods to choose from. The default is maximum likelihood, or ML. This method is generally preferred for its statistical efficiency, meaning it produces smaller standard errors. But this advantage holds true when the error terms are indeed normally distributed. Its main drawbacks are that it can be computationally intensive and may struggle to converge, especially with complex datasets. ML directly estimates both rho and sigma, the correlation between the error terms and the standard deviation of the outcome equation's error, respectively. The alternative is the two-step method, which you invoke by adding the two-step option to your Heckman command. This method is much more robust and will always converge, making it highly valuable for initial diagnostics or when troubleshooting convergence issues with the ML estimator. However, it is generally less efficient than ML and does not provide a direct likelihood ratio test for the independence of the selection and outcome equations. Instead, it calculates rho and sigma indirectly, derived from the inverse Mills ratio. Therefore, for initial model building or when encountering convergence problems, the two-step method is a great starting point. But for final, most efficient estimates, ML is often the target. While the traditional Heckman model addresses sample selection, Stata 15 and later versions introduced a more powerful and flexible command called eregress. This stands for Extended Regression Models, or ERMs. The eregress command is designed to handle more complex scenarios where you might be dealing with endogenous covariates, treatment effects, and sample selection simultaneously. The diagram on the right illustrates how eregress can unify the analysis of these three common econometric challenges. For instance, the example command shown here, eregress wage educate, select working equals children age, endogenous educate equals mother educate, demonstrates how to model wages while accounting for selection into the workforce based on factors like children and age, and simultaneously addressing the endogeneity of education by instrumenting it with mother educate. This unified framework streamlines the estimation of models that previously required separate commands or more complex manual two-step procedures. The first crucial step in any econometric analysis is thorough data preparation and description. Here, we've used Stata's summarize command to get an overview of our dataset. A critical observation arises when we examine the OBS column. For demographic variables like age, education, marital status, and number of children, we have a complete set of 2,000 observations. However, for our key dependent variable, wage, the number of observations significantly drops to 1,343. This discrepancy means that 657 individuals are selected out of the wage data, as their wages are unobserved. This immediately signals a potential sample selection problem. A standard OLS regression on this incomplete wage data would automatically exclude these 657 observations, potentially leading to biased and inconsistent estimates. It highlights why a specialized approach, like the Heckman model, is necessary to correctly analyze this data. Here we see the output from running the Heckman command. The first few lines show the iteration log as the maximum likelihood estimator converges to a solution. The log likelihood values, like -5178, are measures of model fit, and seeing it converge in just a few steps is a good sign that the model is well behaved. The header of the output confirms the model type as a Heckman selection model. It also reports the number of observations used, correctly identifying the total sample size of 2,000. Crucially, it partitions the data into 1,343 selected observations, meaning those with an observed wage, and 657 non-selected observations, which are those without an observed wage. This confirms the sample selection problem we identified in the previous step and highlights how the Heckman model accounts for both groups. Now that the Heckman model has been estimated, let's interpret the coefficients. The output is clearly divided into two panels. The top panel, labeled Wage Outcome, displays the coefficients for our main outcome equation. These coefficients are interpreted much like standard OLS results. For instance, the positive coefficient of 0.98 for Ed suggests that each additional year of education is associated with an increase in the potential wage. Below this, we have the selection panel, which shows the coefficients from the Probit model for the selection equation. These indicate how variables influence the probability of working. Here, we see a negative coefficient of -0.4 for children, which strongly implies that having more children reduces a woman's likelihood of being in the workforce. It's crucial to distinguish these two effects. Children reduce the probability of working, but do not directly affect the wage offer itself. The effect of education, however, appears positive in both equations, increasing both the probability of working and the potential wage. Understanding these individual effects sets us up for the final critical step, determining if the Heckman correction was truly necessary. Now we reach the crucial step, determining if the Heckman correction was truly needed. We look at the parameter rho, which estimates the correlation between the unobserved factors influencing the selection decision and the outcome. Our model estimates rho at 0.70, a significant positive correlation, indicating that unobserved characteristics that make someone more likely to participate also positively affect their potential outcome. The formal test for this is the likelihood ratio test, which assesses if rho is statistically different from 0. Here, the p-value is 0.0000, which is highly significant, well below the typical 0.05 threshold. This leads us to reject the null hypothesis that there is no correlation. Therefore, we confidently conclude that selection bias is present in our data, and the application of the Heckman selection model was indeed justified and necessary to obtain unbiased estimates. Following our Heckman model estimation, Step 5 focuses on post-estimation analysis, particularly using Stata's margins command to interpret the results meaningfully. First, the margins dydx asterisk command allows us to calculate the average marginal effect of each variable on the potential wage, providing a clear understanding of how each factor influences the outcome after accounting for selection bias. Next, to visualize the predicted relationship, we use margins predict y expected at ed equals 10, 1, 20. This command generates predicted expected wages across a range of education levels, specifically from 10 to 20 years.
Finally, margins plot translates these predictions into a clear graph. The plot on the right, titled Predicted Wages by Education Adjusted for Selection Bias, clearly illustrates a strong positive correlation. We observe that as education increases from 10 to 20 years, the predicted wage rises significantly, from approximately $50 to over $100. This graph effectively communicates the impact of education on wages, now corrected for the selection bias we identified earlier. We've covered the mechanics of the Heckman model, but it's crucial to be aware of common pitfalls that can undermine your analysis. One frequent issue is non-convergence. If the model's estimation process iterates endlessly, often described as not concave, it's usually a sign of high collinearity among your independent variables. Another serious problem is relying solely on functional form for identification. This happens if you use an identical set of explanatory variables in both the selection equation and the outcome equation. In such cases, the model's identification hinges only on the nonlinear properties of the Probit function, which is statistically weak and can lead to very fragile or unreliable results. The fundamental solution to both of these issues, and indeed the key to a robust Heckman model, is ensuring you have a strong, theoretically justified exclusion restriction. This means including at least one variable in your selection model that is demonstrably excluded from directly influencing the outcome model. For instance, the number of small children might affect a woman's decision to work, but not directly influence her potential wage offer. This helps the model cleanly separate the selection process from the outcome, leading to more credible results. Now that we've discussed these diagnostics, let's summarize the key takeaways and best practices. To summarize our discussion on the Heckman selection model, let's review some key best practices. First, always understand the potential for bias. Ordinary least squares, or OLS, is inconsistent when data is missing non-randomly due to incidental truncation. Second, it's crucial to explicitly model the selection process alongside your outcome using a two-equation system like the Heckman model. Third, ensure correct identification. A strong theoretical justification for your exclusion restriction is paramount for obtaining robust and reliable results. Fourth, always verify your assumptions by checking the likelihood ratio test for independent equations. If the correlation parameter, rho, is not statistically different from 0, you can safely revert to a simpler OLS estimation. Finally, interpret your results carefully. Utilize post-estimation commands, such as margins, to understand the real-world effects, as raw coefficients alone can be misleading in nonlinear models. Following these steps will lead to more accurate and unbiased findings in your research.